Hello, welcome to Laboratory 2 of MATL 3101. This is the Tensile testing lab, and I'd like to show you today how to perform a tensile test. This is the Q-Test 100 MTS tensile test stand, and this is the device we'll use. I'd like to show you first of all how to assemble the test. Okay, so the first thing you'll need is to assemble the, by the way, this is the crosshead, this is the load cell, this is the part of the machine that when you perform a tensile test converts the force into electronic signal that we can measure. This is the base, and this is the control panel, the electronics, and the DC interface that we'll use. I'll show you more of that in a minute. First, I want to show you where we store the grips and the stuff that you'll need for the test. In this first cabinet, you'll see that there's a lot of equipment in here, but the things that you'll need are two U-joints, which are stored in here. Set these down. Two grips, which are made with threaded fittings. I'll show you why in just a minute. You will need 4 steel pins. I could have had all this laid out before I started the video, but I thought it made more sense to show you where we store them. So you can find them more easily. And the last thing we'll need is conversion fittings. They look like bolts, but they're hollow and they're threaded to receive the tensile test samples. Just happen to have one in my pocket. And so, first thing you can do is find the right size fittings. Before we attach the sample to the tensile test stand, I thought I'd talk a little bit about the shape and size of a tensile test sample. You'll notice that the sample is threaded on each end, and that the center portion of the sample is of a smaller cross-sectional area than the rest of the sample. And that's for a very important reason. When you perform a tensile test, hopefully you know that we're stretching the sample, and we want to make sure that the area of highest stress, which would be in the area of smallest cross-sectional diameter, presumably, and we want to make sure that that area is in the middle of the sample. We do not want the sample to fail in the threaded region, because that would indicate a singularity stress concentration that we could not measure. So we use a sample that has the smallest cross-sectional area in the center, which focuses the stress in that area. And by the way, that cross-sectional area has to be pretty well known. The way you can determine that is to take vernier calipers and measure the diameter of the sample in multiple locations, turning the sample as you go, and then taking an average of the diameter. Now, of course, the cross-sectional area of the sample is the diameter halved into a radius, square, multiplied by pi, but the software calculates that for you, and it will prompt you for the diameter. So measure the diameter in multiple locations, turning the sample as you go, take an average, and that's the value you enter in the software. So, set that aside for a minute. Now I'll show you how to attach the tensile test sample to the machine. Take your conversion fitting, either one, thread the sample into the interior threads in the head of the conversion fitting. thread it in all the way, hand tight, and then thread the other end of the sample into the other conversion fitting. Now, one thing I forgot to mention, another important feature of the tensile test sample is that you have a smooth transition or fillet between the test region and the threaded portion. Again, that's to eliminate stress concentrations or singularities that can cause the sample to fail in application. You want the sample to fail in the center, far removed from the grips, to make sure that we don't have a stress concentration. So that fillet, or that smooth transition, is very important. So thread both conversion fittings onto the sample, and now set that down for a second, and we'll begin to assemble the test rig. First thing you want to do is take one of the grips, doesn't matter which one, and insert it into the larger cylinder on the crosshead. Match up the holes in the cylinder and the crosshead cylinder, and insert a pin which holds it in place. At this point, you can tighten the collar hand tight to make sure that there's no play in that sample, in that arrangement. The next, oh shoot, I messed up. We can edit it, but after I talk about this, let me start over. So now I'll show you how to assemble the test rig, if you will. Set the sample and conversion fittings down for a minute and attach a U-joint. Remember, we have two U-joints. We have an upper and a lower. Attach the U-joint to the crosshead, load cell, that is. Insert the cylinder of the U-joint into the cylinder of the load cell, match up the holes, and insert a pin, as so. Next, you want to insert the upper test grip into the U-joint and connect it with another pin. You may have to adjust the collar down here to make it fit right. There you go. Tighten the collar back up to eliminate any play. Next, attach the sample to the grip, or I should say the conversion fitting, which is attached to the sample to the grip. Make that hand tight. Okay? And then at this point, you'll want to turn on the tensile test stand here on the bottom right, the I button, or the vertical bar, and then raise the crosshead to give you room to attach the rest of the test rig. Make sure that you don't trip the limit switches upper and lower. Next, you want to attach the lower grip to your test sample, to your conversion fitting. Thread that into place. Again, hand tight. Don't put any torque on your sample. And then subsequent to that, take a pin in your right hand and put the lower, or your left hand if you're left-handed, and attach the lower U-joint to the lower grip and insert a pin. Once again, you may have to adjust this threaded collar to make sure that you don't have any, that it will fit. Okay, now we're almost done with the test rig. I want to emphasize at this point a safety issue. When you lower the test assembly, and specifically the lower U-joint, into the base, there is a possibility that you could pinch your hand or finger, or that you could apply unwanted compressive force on your sample. I urge you to avoid either of those situations. Most importantly, don't pinch your fingers on at this pinch point. So safety is the most important thing, although you don't want to damage your sample either. So what you want to do is sit down and carefully lower the test rig, the load cell that is, into place using the arrow down button. when you get close to touching, when the lower U-joint is close to the base, very carefully, just incrementally lower the cylinder into the hole, removing your hand to eliminate any chance of pinching it, and making sure that the cylinder fits into the base without any interference. Also notice that you want these holes to match up pretty closely and have a pin ready to insert. So we're lowering the crosshead a little bit at a time to make sure we don't compress the sample. And there's a little bit of interference there that's just built in, so you just have to overcome that. Very carefully. And then you have to bend down until the holes match. You can also make fine adjustments with this thumb wheel. Very fine adjustments can be made here. So we're going to insert a pin, hopefully. There we go. Okay. And now the test rig is assembled. At this point, you want to make sure that there's not a lot of play in your sample. Adjust the collar on the lower grip down so it's hand tight. Do the same on the upper grip. Okay? And then come over here to the PC. And I'm going to close this. And this is what the desktop looks like. The software is called TestWorks 4. It's located right here, unless somebody moves it. Double click, you'll get the welcome screen and ultimately a username and password. The username is MTS, the password is blank, just hit OK, and it will prompt you for a method. The method we want to use is called MTS EM tension. Click OK. And by the way, if that's not the default, you can choose it here. In a pull-down menu, go to MTS tension and choose MTS EM tension. There's all sorts of methods here that other people have created. This is the one we want to use. That's OK. And hopefully you will see that there is a set of controls on the user interface, and that there is also an indication of the force, which should be dynamic as it is, and you should see the crosshead position, which may or may not be 0. That's okay. And you should see the indication of the epsilon extensometer. We'll talk more about that later. Okay? This little device is the epsilon extensometer. And as the name implies, it measures the extension of the sample while you're performing a tensile test. Now, the extensometer is a delicate instrument, so please take care. It plugs into the back of the MTS electronic box, and it's labeled with a pictorial showing an extensometer. It is in the resting position and can be verified because there is a little pin attached to a tether, which if inserted into the mill location for that pin between the arms of the extensometer, and it indicates the 0 position. In other words, if the pin is not inserted, you can squeeze the arms of the extensometer and you can indicate negative extension, which is only meaningful in a compression test. But if you insert the pin between the arms, right here, then you can compress the arms and it remains in the 0 position, or very close. And by the way, the way you can calibrate that is to gently, and I mean very gently, just hold the arms together, come over here to the interface, right click in that box and choose 0 channel. And now the extensometer is in the 0 position and the indicator says 0. So now gently let go, holding the extensometer by the base, remove the pin, come over here to the sample, run the extensometer behind the tensile test stand, and note that there are 2 spring-loaded clamps and a knife edge on each arm. I should say there is a spring-loaded clamp and a knife edge on each arm. Place the knife edges, insert the pin as before for now. Place the knife edges, hold the spring-loaded clamps back, place the knife edges in the middle of the sample, and with the pin in place and the clamps in the sort of resting position, gently compress the arms of the extensometer. And at this point, the extensometer should be mounted on the middle of the sample, the pin should be in place, and that's it. So remove the pin, and now the next thing you want to do, and I'll show you more about the extensometer in just a minute. The next thing you want to do, is take the safety shield and place it in front of the entire test rig, and then come back over here to the graphical user interface. And there's one more thing, well, there's several more things we want to do, but one of the things we want to do is eliminate any slack or play in the test rig. So watching the force indicator, which is essentially 0, come back over here to the control panel and gently move the crosshead until you see the force go into positive territory, positive numbers. Right now it's about 1 pound. So what that does is I'm gently, very slowly moving the crosshead, and the fact that it's indicating a positive force tells me that there's no play in the test assembly, because any movement, slight movement of the crosshead up results in the indication of force. I hope that makes sense. If I were to move the crosshead up and I got no response here of force, that would tell me that I had too much slack in the assembly. But the fact that I have a positive number tells me that we have eliminated the play in the rig, and we're 1 step closer to the test. Okay? Now, finally, the next thing you want to do is you can go ahead and 0 all the channels. Right click, 0 the force, right click, 0 the crosshead, which is just a measurement of an indication of the crosshead movement. And you can go ahead and 0 the extensometer as well. Now, it may be, it's very detailed, but I think it's very helpful to, at this point, go through the test assistant. So going back to where we were, this is the home screen, if you will, the graphical user interface. Click on Define and Assistant. Now, the test assistant will take you through the entire setup in intricate detail, and most of the steps you can skip over, but it's a great thing to do to make sure that you have everything set correctly, because you don't want to waste a sample. So from the test assistant, just press Start, or just click on the first drop-down item and review each item on the menu to see if you need to make any changes. And if you don't, just next step, configure your units. Do you want, how do you want to measure, what system of measurements do you want? Do you want the English system or the SI system? Metric or English? You can make a global change here from SI to English and so forth. Next step, do you want to use a caliper? No, in this case, because we've already measured the diameter for the caliper, and we're going to enter that information in a minute. Say no. Next step. This is how we're going to measure, well, let's see. This is how we're going to do some calculations. Not really a necessary change. A lot of this is already programmed. Just go through it one at a time to make sure that, for example, the system knows that you're using a round sample and not a rectangular sample or a hollow sample. So make sure it's round. The calculation's already in there. Pi times the radius squared. Next step. Just keep going all the way through. Don't save the method, it's already saved unless you've made changes, which I do not recommend. That's a poor sentence. You don't have to save the method unless you make any changes, and I do not recommend making any changes without your lab instructor's help. But just to go through to make sure that everything is set correctly, you get the right type of sample, the right type of units. Do you want to add the pip marking configuration item? No. Next step. No. Yes, we would like to prompt the user when the test is about to begin. That's an important thing. Say yes. Test is about to begin. Wait for user response. Next step. No. No. Next step. No. Next step. This is the limit detection segment. These are already set to meaningful limits. I would not change these. Next step. No. Next step. This has to do with how the data is saved. Next step. Meter configuration. I wouldn't worry about that. Just keep going. This is the typical curve, I guess, appearance. Okay. Do you want to show an offset yield line? Yes. If you don't have any experience there, the offset yield line is a linear line which is used to mark, I guess, what would be considered the conventional yield point, the point at which the stress-strain curve transitions from linear to nonlinear off by about 1-2%, which is a good indication of the yield point according to conventional standards. No, you don't want to configure the handset buttons. They're already configured, so say no. You don't need to save the method. We're finished. Next step. So you can see that the finish button is highlighted. Go back to test. Everything is still 0. We have eliminated the play in the test rig. We have our safety shield in place. If you think it looks like a motorcycle windshield, you're not the only one. Make sure that's in place before you start anything. The extensometer is in place. Now this is an important point. When we start the test, we have to make sure that as the test progresses, very, very quickly, into, at first, the linear portion of the stress strain, or the elastic portion of the stress strain curve. The extensometer has to be removed before you reach the yield point, or you could damage the extensometer. So what you want to do is start the test, let the test proceed into the elastic portion of the curve very quickly, maybe even after a second or so. You need to pause the test and remove the extensometer, and preserve the data. About to start the test, you start the test by pressing the green arrow to the right. And again, what you should see is a stress strain curve here. The curve should proceed into the linear portion of the curve, and then before it gets to the yield point, we want to pause the test and remove the extensometer. So, start the test. As we planned it, it's prompting us for the diameter of the sample. So at this point, you want to enter the average value of the diameters you measured earlier here. I'm going to go with 0.238, which is nominal, but you use the average you calculated. Press OK. The test is about to begin. OK. There it goes. You may be able to see there's a blue linear line here, and I'm going to pause it before it gets to the yield point. And for the sake of preserving the integrity of the extensometer, I'm going to go ahead and remove it carefully. Notice that we're already at almost 1,000 pounds force. Crosshead has moved approximately 35 thousandths of an inch, and the extensometer reading is here. Remaining behind the shield, reach around and remove the extensometer carefully from the sample and place it on the stand, and come back to the computer and press pause to continue the test. There we go. So you can see that the sample failed in the test region as we planned. Then it broke pretty cleanly, which is normal for this type of sample, steel. So I think we have a good result. Now, the software has prompted us that the crosshead is about to return. I cannot emphasize enough, do not click OK at this point. If the crosshead returns, it will compress the test rig and perhaps damage your sample or some of the components. Before you press anything else, there's no more force on the system. This test is over, okay? So we can simply begin to remove. I would just hold carefully the rig and remove the upper part by removing the top pin between the U-joint and the load cell, and set that part aside. You want to carefully preserve the condition of your fracture surface. Don't touch it. Don't put the two broken pieces back together. Just don't touch the fracture surface, because if you touch it, you could damage it, and we can get a lot of information from fracture surfaces. So at this point, I'm going to remove the lower U-joint assembly. I'm going to try to remove the windshield and remove the lower U-joint and set it aside. Again, carefully preserving the fracture surface. Occasionally, in this lab, the liquid nitrogen bottle will vent, which is normal, but it can be startling. But don't worry about that. That is normal. The air you breathe is 78% nitrogen, so it's not contaminating. It only lasts a few seconds. Okay, so now, because we've removed the test rig, we can return the crosshead by clicking OK. And the crosshead very quickly goes back to normal, resulting in a display of our very nice stress strain curve. And so we're going to do two things here. Now that you've completed the tensile test, there are two things you want to do here. One is save the data. Very important point. So go up to the menu, File, Export Preview, Specimen, and then you will get ASCII data. This is essentially comma delimited values that you can then plug into Excel or some other type program to get the to generate the stress strain curve. So file and save that data on your USB drive, which hopefully you brought with you, because this computer is not connected to the internet, and so you won't be able to upload it or email it to yourself. You need to save it on your USB drive. So once you've done that, the next thing I recommend that you do is save a copy of this image as a JPEG. And that's very simple. Just click right click, save image, I believe. Yeah, there you go. And then save this image as a JPEG, name it whatever you want, save it to your USB drive, and then use that for your report. When you want to do another test, just go back to test and repeat the setup as before. And if you have any questions, please don't hesitate to email me, and I will try to help you any way I can. When you finish all your tests and you've saved all your data, simply exit the program. We're not going to save that file, and that's pretty much all there is to the computer. Then you want to return the equipment to the cabinet, disassemble the test rig, remove your specimen or specimens, or one at a time of course, preserve your fracture surface, place the grips and U-joints in this box, put the pins in this box, sometimes you can't pull the pin out, you just have to push it through. And finally, the additional pins, 4 pins, 2 grips, 2 U-joints, and I left the conversion fitting in the grip. It actually goes in the white box, although it's not a big deal if you forget that part. Close the cabinet, and then clean up your area, remove your samples, and turn the machine off here. O for off. I is for ignition, as Steve says. But this turns it on, this turns it off. And finally, disconnect the extensometer from the back. I don't know if you can see that. Way down low. place it carefully in its box in such a way that you don't put it in a bind. And that's all there is to it. Thank you very much. Oh, I should say that for your lab report, you'll want to write up your lab report with all the segments that Dr. Boo has provided in the handout. You'll want to include your data in both tabular and graphical format. You'll want to summary tables and statistical analysis on the results. Write up a thoughtful set of conclusions and submit your lab report. If you have any questions, please let me know. And thank you for your attention.